gonna pick a particular place where I can apply distribution. So I'm going to pick this one, or I will pick, okay, I'm trying to find one that is kind of interesting to use. I'll use this one. So we are looking at this expression here, okay? So let me just use the cursor key so that we can focus on which expression. Okay, so this is the expression. So when I draw the syntax tree of this thing, what is the last operation? The root node of this tree is going to be the very last operation of what is in parentheses here. What is the last operation here? It's an and, right? So because you have this entire sub-expression ended with not t. Yeah, so the overall operation of what is highlighted right now is an and. So you have an and operation as the root node, because the root node represents the last operation to perform. What is on the left-hand side and what is on the right-hand side of the and. So on the left-hand side, okay, in terms of highlighting the expression, we have basically not s, and then we have an or. So that means we have an or here. The last operation is an or, and then we have the left-hand side and the right-hand side again. So I'm not going to do the simplification because I want to show exactly what syntax tree you should be seeing on line 8 with the highlighted expression. So we have a negation. Now negation is not a binary operator, it is a unary operator, which means it only requires one single component. So what are we negating? We're negating another negation expression, and then that inner negation is applied to S. So on the other side, it is the same thing. So we have not of R, right? And then on the other side, we have the not of T. So this is the syntax tree of the expression that is highlighted on the screen right now. Is that okay? So what does this have anything to do with algebra? The one thing it has to do, what it has to do with algebra is, in terms of distribution, it's looking for the and the or relative to each other like this. That's all it's looking for. So what you're doing in terms of distribution is to look for a pattern like this, and then you're just converting it so that you end up with an or on top, and then whatever you are anding, okay? So you take this entire subtree, we'll call this subtree A, we'll call this subtree B, we'll call this entire thing subtree C. So what you end up doing is to do an and here, and then the and is going to take the subtree A, whatever it is, and end it with subtree C. And then on the other side of the or, you're gonna end subtree B with subtree C. So you can take a picture while you stream it.
Oh no, I'm just video.
Oh, okay. So are we do okay so far with this? So once you look at this entire thing as a tree, it doesn't matter how simple or complicated subtree A is. It is just a single node from the perspective of the OR. And then the same thing applies to B and C. They're basically, each one is only seen as, oh, this is a node in the tree, okay? Take the entire node. And what we do is we replicate the subtree C so that it occurs twice here because we got two conjunctions now. And then we, on one of the conjunctions, on the left-hand side we have A, and then with the other one we have B. So are we doing okay so far with this? I mean, I can only talk about expressions as an expression tree because you are all taking CISP440 or have already taken CISP430. But this is, one way to kind of visualize, the application of the algebraic laws, not only in Boolean algebra, but also in just about any algebra system. this is one way to look at things and understand, when can I apply which rule? Is that okay so far? All right. So getting back, to the screen here,